Okay, so we are in Statistical Rethinking, second edition, chapter 13. We're in the easy questions here, and we're going to do 12E4 and 12E5. Okay, so here's 12E4. So we saw some similar problems earlier, I think in E1 and E2, but we're going to write a mathematical formula for the Poisson regression with varying intercepts. And as I state here, I'm just copying and pasting what I did in it should be 13E. What are we in? Yeah, I got the wrong numbers here. 13E2. So I'm just copying this model, but instead of making it binomial, I'm turning it into a Poisson. So there's nothing really spectacular here. I'm going to pause this and change the numberings, the problem numbering here. Okay, so we're back. Now in 13E5, we're going to do the same thing, but we're no longer using like a hierarchical model where all of the groups, for instance, fit into one cluster, but a cross-classified model. Okay, so the book, even though the question asks us to do a cross-classified model, does not give a lot of detail about it. Okay, so but the detail that is given is in the, right here in the rethinking box at the beginning of section 13.3. And so I think I'm paraphrasing here, but they're like hierarchical models, except that the study subjects are not exclusively nested within unique blocks, but rather distributed among features of the data. Okay, so you remember from the chimpanzee data set example that's kind of been used in this book, each turn, right, each outcome of a lever pull was being classified by both treatment and the chimpanzee and what other thing? The condition, right? And so each unique turn is being classified by several things. Okay, so it's being cross-classified, I guess, is where the term comes from. Okay, so we're meant to do that with a Poisson model. So for that, I'm just going to use the model that I've already used up here in 13E4, but I'm just going to add another intercept here, and then each observation is going to be classified by both group and treatment, right? So we're classifying across different conditions of the experiment and the set of observations. Okay, so you can read all of this, and so here. So I have now two varying intercepts that are cross-classifying the observations, and I've assigned priors to both of the varying intercepts. Okay. Now when I go back and I look at the example that's given in the book, I realize that the way that the author is doing a cross-classified model is to set one of these priors, right, for the varying intercepts to 0. Okay, and the reason that is given is to avoid overparameterization. And so I think that even though the question doesn't ask for it, I think it's important that we explore this because I also kind of want to explore this for myself. Okay, so we could okay. So apparently this model right here leads to overparameterization, and we'll talk a little bit about it. But basically, I think where the problem or possible problem is arising from is that we have this intercept here. We have two varying intercepts, but they are combining to create, call it our baseline value for log lambda, right? But because they're both parameterized, or because they both have a mean, well, if I nudge. Let's say that they sum up to be 2 or something like that. Well then the estimate for a group could be 2 and a treatment could come out to be 0, or this could be 4 and this could be -2, or they could both be 1. In other words, there's many ways to get the same value for the baseline value. Okay, I think that is where the overparameterization is coming from. If you have a better understanding of this, then please leave comments. That would be very helpful. Okay, so the way that the book would do this is to set one of these priors to 0. I'm actually not really sure how that overcomes the problem because this is just the prior. Um, anyway, I'm not really sure how this overcomes the problem. Um, but another thing that I don't like about this parameterization is that it doesn't feel super intuitive to me, um, because it's kind of handicapping in a way one of these intercepts. Okay, but I might want, like uh, a less biased estimate for alpha treatment here. But I've already biased it by putting it here to, some arbitrary value that is not going to be estimated. Um, and so I think that another way that we could do this instead is to set a universal intercept alpha and estimate that, and then also have intercepts for group and treatment that are not hierarchical, um, and then we can interpret the alpha group and the alpha treatment as deviations away from kind of this universal intercept. So I hope that you're following me so far. Um, but even at that, so I guess I would prefer this type of parameterization. But even at that, there may be times where we want this type of parameterization, right? Where we want to know, okay, what is our best estimate for the effective group or the effective treatment, right? So anyway, so I want to explore this overparameterization idea. And so what I'm going to do is I'm actually going to code up each of these models and look at and try to see if the overparameterization is causing the problem. The reason that I'm skeptical of it causing a problem is because in, what is that? I think in section 11.1 or 11.1, there's an example where where one of the models is overparameterized, but everything works out fine. Okay, so okay, I think I've said enough about that. And my point is not to deliver a speech about or a lesson about overparameterization, but rather to try to understand what the problem could be with experimentation. And so that's what I'm going to do. Okay, so what am I going to do? So I've generated some fake data here, okay, where I've assigned values for groups and alpha group and the alpha treatment, right? And so I've created Poisson data that has a mean and variance of my linear what do you call it here? My linear model, okay? And I've wrapped that into a data list, okay? And so now I am just going to code up these different models. And so here I have the overparameterized model, okay? So this should correspond exactly to this, okay? And I've already ran it, so we won't have to run it again. And then here is the next model, okay? Where we set one of the priors here to 0. And so here I think I'm setting alpha t treatment to 0. Okay. And then, there we go. And then I have the model that has the universal intercept. Okay. And so I run all this. All right. Okay. So first I want to look at the outputs of all of these and compare them to what I know to be the values for A group, A treatment, and beta X, okay, because I've hard-coded these values in the data up above, okay? And so these are the pricey outputs for the three models here, okay? But notice that the only one that we should expect to maybe correspond to the hard-coded values is the overparameterized model, right? Because, we hard-coded the values in a parameterization that mimics this model here. Okay. So now when I compared, say the effect or A group and A treatment, right? So the first group is 0.9 and the second group is 1.1, and same for the treatment 1 and treatment 2, and we see that for the group that this is maybe directionally correct. It's not really clear with the other one, right? And beta x should be 1, and here it actually is. Okay, so it's not really clear how well this model is doing. Like I said, the other two models, it's not really fair to compare, their A group and A treatment to this, and so to the hard-coded values. So instead, what we're going to do is extract samples from each of these posteriors and then build up the predictions of each of these models, okay? And so that's what I've done here. So I've extracted samples from all of these, Okay, I've generated an x-seq value, and then generated the actual values from the hard-coded, the hard-coded data that should be expected given the parameter values here. Okay, and now I'm going to plot each of the models for all 4 conditions. Group 1, Group 2, with treatment 1 and treatment 2, right? So there's 4 total conditions here. So here's model 0, the overparameterized model, with Group 1, treatment 1, Group 1, treatment 2, Group 2, treatment 1, da, da, da. Okay? So I've done that for all of the models. And now I'm just going to simply plot those models on top of one another to look for discrepancies. And then I'm going to further plot what should the hard-coded data, okay, what the hard-coded parameters would suggest the data should come out as. Okay. All right. So so here this is just me plotting everything. Okay. So notice that the first plot for model 0, the overparameterized model, is going to be color-coded in black. Okay, and it's going to have its own probability intervals, credibility intervals plotted. Okay, and then for M1 that will be red, and then for M2 that will be blue, and then I'm plotting the hard-coded expected values in green. Okay, so so I do that for all 4 conditions: G1 T1, G1 T2, G2 T1, G2 T2. Now when I plot these, let's zoom in on this. Okay, so when I plot these, you'll notice that so let's look at these. So the green is the expected value, the expected by hard-coded values, and then everything else are the different models. But notice that the models, we have red, blue, and black, but they all completely overlap as far as we can see, kind of making this nice purple color. Why? Because all of these models are equivalent in terms of their posterior predictions here. Okay, and then further you can see how well the model did, at least given the data that it was provided in predicting the hard-coded values here. Okay, so the moral of the story is that all 3 of our models were equivalent, maybe not in terms of how we would go and interpret them, but in terms of their posterior predictions, so that they were all equivalent. So what was the difference? What was the possible problem that was raised by the overparameterization? Well, I kind of skipped by it the first time, but it's this. I believe that it's this right here. Now, it wasn't a big problem here, but in this first model, in the overparameterized model, the model had a little bit of difficulty running. Okay, so we had some divergent transitions and maximum tree depth warning, which isn't really always a big problem, but it suggests that the posterior space is maybe a little bit too, how do I want to say, it's maybe too broad to be explored thoroughly. Okay, so you see that the chains had some problems, running in this particular model, and that was not the case. Well, I guess this had 7 divergent transitions, but far fewer than the first one, and then the second one I think had just very few. So I think that the problem that overparameterization is causing in these cases is just how well the chains are running. I believe that is the problem. Okay. All right. I think that is it for this one.